So let's take a look. Your first page of the notes should be a graph like this. So if this is the function, is this function continuous from end to end? Yes, right? No corners, no holes, no breaks, no holes, no gaps, no asymptotes. Is this function differentiable? Where is it not differentiable? Okay, it's not differentiable at this corner, and it's not differentiable at that corner. It is differentiable at the endpoints, because endpoints aren't corners, but it's not differentiable at those things, okay? So if I want you to graph the derivative for this, remember that the word derivative is just synonymous to the word slope. And so you can say, all right, I also understand that that means graphing the slope. So this function has how many different slopes? Three different slopes, because there are three different sections. Okay, what if this was curved? How many different slopes would the function have? A lot. How many? Infinitely many. Okay, you'd have infinitely many slopes along a curve because every single point would have a different slope. But here I only have three different slopes. And so the way we set this up is we say, all right, we're going to have a slope that extends from the end point of -4 inclusive, so I include the end point, up until the 1, but I don't include 1 because 1 doesn't have a slope because it is a corner. So I'll have one slope that goes from that segment. Then I'll have another slope that picks up at 1, and not including, and then going up to the number 2. So that will represent the next segment. And then I'll have a third type of slope that takes over at the number 2 and goes up to the end point inclusive of 4. Okay, yeah.
Is it -1?
Yes. I think I said it but didn't write it. We can listen to the recording. All right, does anybody have an idea for the first segment what the value of the derivative would be? 1. Because I'm really asking for the first segment, what is the value of the slope? And so I'm asking you, what is the value of the slope on this segment? The value of the slope is 1, and so the value of the derivative is 1. For the second segment that connects the two corners, what's the value of that derivative here? I'll make it green. Okay, that has a derivative value or a slope value of 0. And then finally, the last segment that's going down, if you count its slope value, what do we get?
-2.
Okay, down 2 over 1, down 2 over 1. And so we're going to have -2. So then when you want to make a graph for that, it will look like 3 constant pieces, 3 distinct, not continuous pieces. And so it's going to look like this, from -4 to -1, I will have a value of 1. That is a horizontal piece that is constant. It has a constant slope, so the graph must be constant. Then from 1 to 2, I have another constant slope. Its value is 0, so it will be open connected to open. So those are 2 open-ended circles. And then -2 is my last constant slope, so I'll drop down to a value of -2, and until I get to the number 4, then I will have a closed circle on the end. So you've got the non-differentiable spots have 2 open circles because they're not differentiable. They represent a corner, and the other represent horizontal pieces. Any questions about that? Going from linear pieces to constant pieces that are steady. So then the question is, can you go the other direction? So now, if I give you the derivative, could you create a continuous graph from that information? So draw a continuous function through 0, 4. So if we put 0, 4 on here, and we know it's continuous, so it's going to be a closed circle because we were told it was continuous. And then you look at what you're given. Symbolically, we are given f prime, which means we are given the slope. And so what that tells us is that the slope should have a value of -1 for the whole left side of the graph. Anything less than 0, I should have a value of -1, approaching that point that I have on there. Now that I've got 0, 4 as my point. So I need to have a graph that has a slope of -1. Okay, that slope coming down has a slope of -1 approaching that point 0, 4. And then after that point 0, 4, I need to have a slope of +1. I switch slopes because the value switched constant values, and now I'll have a slope of +1. So I've created an absolute value. It's a continuous function. It's not differentiable because it has the corner, but it still met all the criteria. Okay, any questions about that? Okay, you'll have to learn how to read graphs, so we're practicing about that. Okay, so now our vocab. We've got the slope of the curve, we've got the rate of change, we have the word instantaneous, we have the word derivative, and now we're going to introduce the idea of velocity. And velocity is also synonymous to all of those other things. Okay, the velocity can be determined by the slope of the curve. The velocity is the same thing as the instantaneous rate of change. Velocity can be found by calculating the derivative. It's all the same. You'll just find in calculus that you're going to do a lot of the same things. You're just going to be asked it 5 different ways. So you got to be comfortable with all the ways they can ask you to find something, and it's all the same kind of math. So in physics, we define position as the original function. So it could be defined as f of x, it could be defined as p of t, it could be defined as h of t. The original function is always what's given your position. If you're talking about, sometimes you're only talking about vertical, so it could also be height. That's a type of position. The average velocity, now watch out for that word because they're going to throw that word in there again. The average velocity is not calculus. Average is simply f of b minus f of a over b minus a. So don't get sloppy. Make sure you're reading for the right words. When they put on instantaneous, or even velocity by itself without the word instantaneous in front of it, as long as it doesn't have the word average in front of it, now we are moving into calculus world. Okay, so instantaneous velocity is going to be the limit of this, which we now know that the limit as b approaches a, that this is f prime. Okay, so we can use prime. I do not expect you to go back to the limit definition anymore unless I'm specifically asking you to use Newton or Leibniz to prove it. Otherwise, I want you to use all your rules that you have. Use your product rule, quotient rule, power rule. Use all those rules that you have available to you. So if in physics you define your function as a parabola, then the average velocity along that parabola would be 16b squared minus 16a squared over b minus a. That is the average because it doesn't involve a limit and it's over a specific interval period of time. The instantaneous velocity is going to be the prime, and so it would be y prime. And the y prime on 16t squared is 32t. If you know anything about physics, you know that 16 and 32 are important numbers in physics, especially because it's due to the value of velocity, the value of the acceleration due to gravity, but measured in feet per second squared. So 16 and 32 are important numbers. If you're in meters, you'll recognize that it should be 9.8. All right, so let's get these official displacement. The displacement is the difference between where you started and where you end up. Okay, displacement, the difference between where you started and where you end up. And so it is simply the subtraction of f of b minus f of a. It doesn't have a denominator, it's a straight out subtraction. Most people, if they get this wrong, it's because they assume that where they started was 0, and you don't always start at 0. You might start off of the diving board, so you're starting up high, where you're not starting on ground level. So displacement f of b minus f of a. Average velocity, f of b minus f of a over b minus a. So it's the division that changes it from displacement to velocity, average velocity, the division of that. And then instantaneous velocity, we've seen this already. The definition is the inclusion of the limit, which we now are going to call f prime of time. Okay, so watch your words and watch your vocab. Okay, so a projectile launched upwards from the surface of the earth follows the height of negative 4.9 t squared plus 120 t meters after t seconds have passed. Find the displacement after 5 seconds. So the displacement is going to be s of 5 minus s of 0. Don't just get lazy and assume it's going to be s of 5 by itself. You also have to take into account s of 0 because that could impact the displacement, but it's the height at the end subtracted from the height of the beginning. All right, so you, if you haven't, go ahead and grab your calculator. Some of you have them out already. So we'll be doing negative 4.9 times 25 plus 120 times 5 minus or plus 4.9 times 0 minus 120 times 0. So somebody can plug that in. And we do have some zeros here that we're using, and then we're going to get 25 times negative 4.9 plus 120 times 5. Anybody got that? 427.
477.
477, thanks, 0.5. All right, and in physical situation questions like this, I will require units. That's part of that standard to know the context. And so if we're measuring displacement right now, it's simply a measurement of the distance traveled. And so this is going to be measured in the unit of meters. And so you'd want to include meters. Okay, the average velocity is take that same number, that s of 5 minus s of 0, and now you're going to divide it by the interval 5 minus 0. So you're going to be taking 477.5 with the unit of meters, and you're going to be dividing it by the interval of time. And what is the unit for that interval of time?
5 seconds.
Seconds. Okay, if you look up here, it always will tell you. And so this would be 5 seconds. And so then you'll use your calculator to figure out the numerical value, but you'd also have the units. And the units are going to be meters per second. So what do we have for an average velocity? 95.5. And then that would be meters per second, which is a velocity unit. And then the last one says find the velocity at 5 seconds. Now notice the word instantaneous isn't there, but it is implied. If it's just plain velocity, the implication is that they want instantaneous velocity. So we want s prime of 5 this time. So now we want to find s prime, and using our power rule, this would be negative 9.8 t plus 120. That's the derivative using the power rule, and the 120t derivative is 120. And then we'll plug 5 into that. So negative 9.8 times 5 plus 120. So let's see, 80 something? What do we get?
71.
Oh, close, 71 point, nothing? 71 on the dot?
Yeah.
71, but the units are still the same if we're measuring velocity. Meters per second.
That's basically saying at 5 seconds is velocity.
Right. Now its average velocity was 95.5 meters per second. At the very end, its velocity was 71 meters per second. So if the average was 95.5, what does that tell you that this projectile had to have been doing maybe towards the beginning?
Going fast.
going faster than 95.5, because if you're ending slower than 95.5, you have to have some faster speeds that would balance it out. Okay, then asking the question, when is the projectile at rest? So again, this is another way to ask a calculus question. When is the projectile not moving? That's what at rest means. It means it's not moving. And if it's not moving, it has no velocity. The velocity is 0. And so it's asking us to take the velocity expression we found just prior and set it equal to 0 to find out when it's at rest or when it's not moving. So my S prime of t, which turned out to be negative 9.8 t plus 120, I'll set that equal to 0. And then I'll solve that with my mad math skills. Okay, and using division, negative 120 divided by negative 9.8. This is going to give me a unit in time, and so I'd want to make sure that I had my time unit on here. All right, so negative 120 divided by negative 9.8, what do we got? 12.2. 12.2 what? Seconds. Okay, so after 12.2 seconds, it is at rest, no longer moving. Any questions so far? Yeah, Zach.
So why do you find the derivative this way?
Because the key is that the only thing we know is that the velocity is 0, and the velocity is what is measured by the derivative. That's what at rest means, is the velocity at 0. Okay, describe the yeah.
Do you want us to use this kind of annotation even if we could just use like the physics equations?
Yes, because we're going to be dealing with a lot. Yeah. Yeah. I'll understand what you mean, but you'll see this more commonly like in our book and stuff. Okay. All right, so describing the motion of the particle. This is at rest at 12.2. Describing the motion is what does it do before 12.2 and what does it do after 12.2. So when you want to talk about the projectile, you first need to know about the at rest. So that would be first thing. So first find the moment of rest, which we already did, which was 12.2 seconds. Then you want to find out what is it doing before 12.2 seconds and what is it doing after 12.2 seconds. So we want to compare the velocity before and after. So here's a technique that you'll see a lot. You'll see before set up as 0 to 12.2. And then you'll see after as 12.2, anything after that. And usually you'll see it kind of set up like a little chart like this, and we're looking for the velocity. The thing that's true about objects in motion is once you've found where they are at rest, before that moment, their velocity will all be the same kind of velocity. It'll either all be positive or it'll all be negative. And then on the after rest, the same thing. It'll either be all positive or all negative. So you do a test case. Pick me a number between the time 0 and 12.2. 1, great, okay? 1. Check the velocity at 1. So how do I check the velocity at 1? Well, remember our velocity equation was negative 9.8 t plus 120. If I check the number 1 in that velocity equation, what kind of number do I get? I don't need to know what it is. I just need to know what kind of number it is. All right, what if I check the number 2? 3, 5, 9, 12? Okay, when's it not going to be positive anymore? 12.201, something after. So this will always be positive. Anything after, okay, if I check 13, 20, 100, anything after that, I'm going to have a negative value. That helps me describe motion, because if I know that velocity is positive, then the motion is going in what direction? Up. Positive velocity means my thing is going up. And negative motion, negative values mean my thing is coming down. You ever seen those old Looney Tunes, Bugs Bunny, commercials or cartoons where the thing like shoots and then like hangs there and suspends in midair and then finally drops? Okay, that's the moment of rest we're talking about. It doesn't last very long, it's instantaneous, but that is the motion. So positive motion is associated with up and negative motion is associated with down. So if you were to describe the motion and you were to write it for me, you would say from 0 to 12.2 seconds, the projectile is moving up. From after 12.2 seconds, the projectile is moving down. How do I know it's up and down? Because the problem told me it was shot upward. Okay, if I was doing a Pinewood Derby car or something that was going on mostly on a flat surface, well, it comes down a little bit, but you might say it was going forward or backward or left and right. Okay, any questions about that? Okay, let's define speed. Speed and velocity are two different things. Velocity includes direction, speed does not. So velocity is straight out f prime. Speed is the absolute value of f prime. When would velocity and speed be the same thing? If they're both positive. When would velocity and speed be different? If the velocity was negative, and the speed is always positive. Okay? You say I was speeding and I was going 83 miles an hour. You don't say I was speeding and I was going negative 83 miles per hour just because you were going south on the freeway. All right? Speed is always a positive number. All right. So that brings us to acceleration, which did pop up on your homework a little bit, but just the acceleration is the second derivative, so you're moving through that. The units for acceleration, if you're using what's called English units, you'll be using 32 feet per second squared if you're talking about gravity. So these are the values that represent the constant of gravity. If you're metric, it'll be 9.8. Typically, that's also accompanied by a negative to indicate that this is pulling in a downward motion. This is only gravity on Earth. And actually it's only gravity at sea level on Earth. Gravity is slightly different if you are at a higher elevation or even at a lower elevation. It's negligible. You're not going to feel it a ton, but if you go to another spatial body like the moon or Mars, or you would have a different value for gravity. Then the idea of what's called jerk. Jerk is the third derivative. So jerk would be f triple prime or d3 of s over dt3. That's the third. Jerk is literally what you feel when you have a large amount of acceleration. Okay, so if you've ridden Incredicoaster or if you've ridden the accelerator or any of those, it's that you feel that jerk. Or when you, if you are involved in a car accident or you have to slam on your brakes and you decelerate really fast, you experience jerk because that is happening at such a rapid rate. So when the change of acceleration is happening very rapidly, whether that's decelerating or accelerating, you would feel the jerk feeling. And what would you think the measurement of units would be for that? Meters per second cubed, or feet per second cubed. Okay. All right. Now, in English, we also have the phrase speeding up or slowing down. That's what we say in English. Again, that's a feeling that you have when you combine the feeling of acceleration and velocity together. So speeding up is the combination of same sign velocity with acceleration. By same sign, I mean both of them are both positive numbers or both of them are both negative numbers. You experience speeding up when both of those are positive. My favorite double negative example is the person who jumps out of an airplane. Okay, the person who jumps out of an airplane is experiencing negative acceleration. Why? What's affecting them? Gravity. Okay, so they're experiencing negative acceleration, but they are also experiencing negative velocity because their direction is going down. But as that person is falling, they are experiencing speeding up because they are getting faster and faster and faster and faster towards the ground. So even though they're having both negative experiences, negative forces that are working on them, the feeling is speeding up. That's what we say in English. So you're always looking for a combination of same sign. If we are slowing down, it would be the combination of opposite sides. So either one of them is positive, one is negative. Doesn't matter which one is which, but opposite sign velocity with acceleration. And mathematically, the best way to find this is to make a comparison chart where you're looking at acceleration and velocity compared at the same time. So I'll kind of show you how to do that. All right, so here we go. Find the speed at 5 seconds for this same projectile we were working with earlier. Well, we know that speed is based on velocity. So if we find velocity first, and it's still negative 9.8 t plus 120, the speed is going to be the absolute value of that. So the speed will be the absolute value of whatever we get for velocity. So let's figure out what we get for velocity. We have negative 9.8 times 5 plus 120. I feel like we came up with that earlier. It was like 71 or something like that. Negative 71. That's the velocity. The speed is positive 71. And those are both measured in meters per second. To find the acceleration at 5 seconds, you're going to take the derivative again. And the derivative of negative 9.8 times t is the constant negative 9.8. And the derivative of 120 is 0. So we get negative 9.8, which is the constant. That's the constant due to gravity. And then that would be measured in meters per second squared. So to answer the question, is the projectile speeding up in our English vernacular or slowing down at 5 seconds? Well, we look at the combination of the velocity and the acceleration, not the speed and the velocity, not the speed and the acceleration, the velocity and the acceleration. So since v equals negative 71 and a equals negative 9.8, those are considered to have the same sign. So yeah. Oh, positive 71, thanks. I was just trying to do that from memory from last time. All right, so it's positive, thank you. All right, that changes our answer. So since v is a positive number and a is a negative number, then we can say the projectile is slowing down. Okay, so yeah.
Why is v not negative?
I just did the math wrong. I was doing it from memory. Okay, any questions on that? So on the upcoming quiz, it could be, is the projectile or is the object speeding up and slowing down, and why? And then you would have to give me the justification. Pick one, speeding up or slowing down, and then tell me why it is, because it's a combination of two things that have the same sign, or they share the same sign, or they have the opposite sign. All right, so now let's talk about what it means to be going towards or going away. So we've already talked about speeding up being same sign We've talked about slowing down being opposite sign. Velocity with acceleration. Velocity with acceleration. When you're going towards something or going away from something, it's also checking on the same sign or the opposite sign, but it's velocity with something else. It's velocity with position. And for some reason, this one seems to be tricky, that people have a hard time with that. Okay, it's the combination of velocity, not with acceleration anymore, but it's the velocity relative to its position. All right, and so that would be the first thing I'd want you to do, velocity with position. And for going towards, you're going to have the opposite sign. And for going away, you're going to have the same sign. All right, so the way I think of this is I picture a number line. And I picture the velocity with the position. So let me show it to you on the board. All right. Okay, so is the projectile going away or towards the ground? So ground would be ground 0 at 2 seconds. And so we want to compare the velocity with the position at that point. And so we would want to know the position at 2 seconds. So that's negative 4.9 times 2 squared plus 120 times 2. You do not even need to know what that's going to turn out to be. I just need to know if it's going to be positive or negative. All right, so if I take 2 and I multiply it by 120, I'm going to have a really big positive number. And the negative 4.9 is not going to be enough. So this is going to be a positive value, and that's really all you need to know. Okay, since the position is positive. And then the velocity would be the derivative of that. So negative 9.8 times 2 plus 120. Okay, that also looks to be a positive value. So since both the position and the velocity are positive, then relative to the ground, the projectile is going which way? Away from the ground. And then at 5 seconds, we would check again. So the position, negative 4.9 times 5 seconds plus 120 times 5. Okay, well again, I look at that and I'm like 120 times 5, that's 600. And then negative 4.9 times 25, that's not really enough. So this is still going to be positive position. And then my velocity would be the derivative, negative 9.8 times 5 plus 120. Okay, so how about negative 9.8 times 5 plus 120?
No.
Positive.
Still positive. Okay, so same thing, still going away from the ground. All right, any questions on that? Okay. All right, so that finished up